Hi, in this video, I'll be going through how differentiation is used to determine certain properties of the graph. And then we'll move on to now applications of differentiation. We have already learned what is a derivative function and how we can differentiate functions and find the value of a derivative which is equal to the gradient of its tangent line at a point. Now we'll see how differentiation is used for other purposes. Before that, we need to define some definitions to get us started. So, something about a function is known as the maximum and minimum value. From the name, you already understand that the absolute maximum just means that it is the greatest value that the function can achieve, so that all other values within the domain is less than it. And the absolute minimum is the smallest value. They are also known as the extreme values. And from this graph, you can see that it has two absolute minimum value and one absolute maximum. But for the other, it has 1 at minus pi over 2 and 1 at pi over 2. And then there's an idea of the local maximum, which is if you're just given a certain interval and it is the maximum value within that interval, then it is considered the local maximum. A similar definition occurs for local minimum, and we can look at an example to understand all these maximum and minimum values at one glance. Take for example this quintic graph from -1 to an arbitrary value. This -1 point is considered the absolute maximum because across the domain which is being defined, it is the greatest value. And this 1 point is known as the local maximum. It is not the absolute maximum because it is not the maximum value within the whole domain, but it is just the maximum value within an interval. And so that's why it's considered a local maximum value and not an absolute maximum value. And so, why do we care? Well, this is our first major theorem. However, the proof is omitted as it requires more technical skills from analysis, real analysis, which we will not go through in this video. But this is known as the extreme value theorem. It says that if f is continuous within a closed interval and differentiable, then f attains both absolute maximum and absolute minimum within that interval. The idea is that there exist actual points for the functions to hit this minimum and maximum value. So this less than or equals to is really it can equal to m. And then f will take all the values within this interval since it's continuous, so you don't break. There's no breaks. And you can see why these conditions are necessary. If it's not continuous, then it doesn't attain the absolute maximum over here. And if it's not a finite interval, then it doesn't attain the minimum values at 0. And if it's not closed, means it doesn't reach the end. And so you can see why these conditions are needed, so that when you state the theorem, it holds. So the idea that is, you just need to remember that if you are continuous on a closed interval your function, it is able to hit its absolute maximum and minimum. With this theorem now, it gives us problems that we can solve, such as the extreme value problem. It just allows us to find where the absolute maximum and minimum are for a graph, because you know they exist, so you just use numerical methods to find them. And the idea is just you evaluate them at the endpoints and then find the local extreme values and see which is the largest. And the largest will then be the absolute maximum and the smallest is the absolute minimum. So now the question is, well, you can use a very simplified way to find these extreme values locally. The real question now is, how are we going to find these local extreme values? Is there a way? And yes, there is. And now we'll build our understanding to reach that. So, to give some idea, we need to define this thing called a critical point. It's just a point where the derivative does not exist or equals to 0. And if it equals to 0, it is known as a stationary point. So all stationary points are critical points, but all critical might not be stationary. An example is if a graph has a vertical tangent at one of the points, then it is critical but not stationary. And we can use the first derivative to determine whether it is a stationary point. And so this is not the first derivative theorem for local extreme values, and that if you are local maximum minimum, then and your derivative is defined, then your derivative is 0, meaning your point is a stationary point. How do we prove this? Well, the book has a proof and I'll go through it now. We'll prove why the only number that it can be is 0 and cannot be positive or negative. Say you are a local maximum at the point. So fx minus fc is always less than 0 for all values near c. Then the limit from the right is also less than 0, because x minus c is positive and fx minus c is negative. But the limit from the left will be positive now, because x minus c is negative. And so, if you combine these two equations, since the limit exists, fc equals to 0. And this is also proven the same for the minimum side. Thus, this gives us a way to determine our local extreme values. Because we take the converse, it means that if we take the points that are not causing fc to be 0 or fc to be defined, then f cannot even be a local extreme value at that point. So the only possible ones are to try out those that are equals to 0. And that is why when we do for the absolute extreme value, these local extreme values, we can test it by just finding points where the derivative is 0 or does not exist. Meaning we can change 2 to finding critical points. And then we just compare which is the largest to determine the absolute. While the converse might not be true always, we will then determine a way to prove that given under certain conditions, when fc equals to 0, it can allow us to show that it is the maximum or minimum value at a certain interval, meaning it's a local one. But for now, we can take the idea that f being a local maximum must mean that fc equals to 0. And so what I've said is known now as the closed interval method for finding absolute maximum and minimum values of the function. Here's an example for you to see how you can do it. So, within the interval, we check the values at the endpoints, -2 and 1. We find the critical values, and then we just compare and determine that the maximum value is 4 at -2 and the minimum is 0 at 0. Now, we move on to Rolle's theorem. Given the conditions that it is continuous, differentiable in the interior of the interval, and fa equals to fb, then there will exist a c such that the derivative is 0. The idea is this stationary point now can be considered a turning point, because if fa and fb equals to each other, there must be a point where it comes back unless it's the constant, and if it's the constant, then fc is 0 already. So the idea is to capture this turning point, and the proof follows that if it's constant, fc is 0, so we can take that out. And if it's not constant, the absolute mean cannot equal to the absolute max. If that is so, then every value inside is the same, and then it's the constant. But since it's not a constant, the absolute mean does not equal to the absolute max. And so by the extreme value theorem, f attains the extreme values on this closed interval, but it cannot be both fa and fb at the same time, because fa equals to fb. And so it must attain an extreme value somewhere in the interior, and this is a local extreme value. And then by what we have went through, if it's a local extreme value, fc equals to 0. Hence, we found a point where fc equals to 0, meaning there's a tangent line horizontal to the graph. And with this idea, we get to generalize it to the mean value theorem, which is also considered the slanted Rolle's theorem. And so the hypothesis is still the same: you must be continuous and differentiable. Then there will exist a point such that it is equal to the gradient of the line connecting the two endpoints. And the idea is just to shift this graph. Imagine a graph horizontal like this, and then now you just shift it upwards by like maybe moving an endpoint, and it goes into this graph. We can shift it back by deleting away this line, by translating it with this line. Then the endpoints both become 0, and since they are same value, there will exist a c such that f prime c is 0. If you differentiate this top expression now, f prime c is 0, which just means f prime c equals to fb minus fa over b minus a. Oh, sorry, earlier I meant h prime c. And so you found a point such that it is equal to the gradient of the secant line, hence proving the result. And so you can see how we have used the extreme value theorem to help us prove the Fermat's theorem, which then helps us prove Rolle's theorem, and now the mean value theorem. And the mean value theorem is really important, as it shows the existence of a value on such that the derivative of the function is equal to the points connecting the endpoint, the gradient of the secant line of the endpoints. And with that, we come with the corollary that if your derivative is 0 throughout, then it is just the function is just equals to the constant function, and we don't need an integration to prove this, but it actually comes from the mean value theorem. Because if we just take any 2 points and there exists a value in the interior such that the derivative equals to fx1 minus fx2 over x1 minus x2, and then if this equals to 0, it means that fx1 equals to fx2. And so x1 is arbitrary, and hence fx equals to c, where c is some constant. And with that, we then now prove another corollary, which is if the gradients are the same, then there will exist a constant function linking the two functions together. And that makes use of the idea that f minus g is now just the constant function on AB. Because if you just take the derivative of f minus g, it will be 0. You apply this result from corollary 1, which equals to a constant, means f minus g is a constant, so f equals to g plus c. And that's why when integrating a function, you usually add a constant at the end. So this video wraps up, and we have already went through certain theorems that will help us build our understanding on how we will apply differentiation to more problems. Thank you for listening, and I'll catch you in the next video.